Thank you, Mark, for the introduction. So today, my talk is about designing systems for at-scale recommendation. But what I really want to do is for you to re-examine the algorithmic and systems building blocks used in this field. So I want you to think about how we can co-design the way in which we represent information with underlying hardware platforms to ultimately create better and more accurate at-scale solutions. To recap how recommendation is done, it takes in concepts about users and content, maps these concepts to dense vectors called embeddings, then feed these embeddings through DNN stacks to generate recommendations. And state-of-the-art models like to store and represent these embedding vectors as tables. Unfortunately, when we have billions of users and unique pieces of content, we end up with terabyte-scale models that really limit the scope of feasible hardware solutions. In this talk, we revisit the embedding representation component by exploring it as a design space and thinking about how we can co-design representations with underlying hardware. For the rest of this three-part talk, first we go over our proposed hybrid representation that uses both memory and compute to generate high-quality embeddings. Next, to exploit the diverse system requirements of representations, we evaluate the compatibility of GPUs, TPUs, and IPUs. Lastly, we go over MPREC, our proposed multipath design that uses heterogeneous mappings between representations and systems platforms. First, let's start with representations. So our default representation is embedding tables. And if you've seen some of the previous talks earlier in this conference, people have been optimizing for embedding tables. So embedding tables treat sparse features as lookup indices for individual entries. The table's values are updated during training and then accessed during inference. While embedding tables provide a good baseline accuracy, they scale to terabytes in size. So a memory-efficient alternative is called deep hash embedding. And in deep hash embedding, sparse features are first fed through encoder stacks to generate floating point vectors. These vectors then pass through a decoder stack to become embeddings. So during training, we update the decoder parameters, and during inference, we dynamically generate the embeddings. So from a capacity angle, we end up with small models in the megabyte scale, since we only need to store the hash functions and MLPs. But from a latency perspective, we end up with a ton of more flops. So based on the differences between these two approaches, we propose a hybrid representation that uses both execution paths to generate higher quality embeddings. So for here, we concatenate the semantically different embeddings and train them end-to-end with the recommendation model. And of course, executing this will incur heavy memory and compute resource usage. Now let's see some characterization highlights. So first, we want to see how the representations stack up in terms of model size and accuracy. So our baseline is a Criteo-Kaggle use case, which is a medium-sized recommendation benchmark. And when we consider different configurations of the representations we just saw earlier, we see a new design space. So the default ones are used embedding tables. So in here, each red point is a variant of deep hash embedding with slightly different MLPs and hash functions. Purple points are for hybrid. Yellow points represent when only some tables are replaced with deep hash embedding. And blue points are our baseline, which are the default embedding tables. So now we see unlocking a new design space here. So we see that DHE configurations lead to aggregate model sizes that are 2 orders of magnitude smaller. This is because DHE only requires a small shared set of hash functions. On the contrary, hybrid configurations achieve accuracy improvements on the scale of 0.1%, which ironically is considered significant for a recommendation use case. But what are the costs of DHE and hybrid in terms of latency? So in here we show the execution time breakdowns of these representations for both CPUs and GPUs. So for using tables, we see that execution time is dominated by embedding time lookups. When we pivot to DHE, there's approximately a 5 times slowdown for GPUs that originates from 2 orders of magnitude more flops. And then hybrid exhibits the worst execution time since both memory and compute paths are used for all sparse features. And since these representations cover such a wide range of system requirements, we thought this could be a potentially good fit for different custom accelerators. So as we saw earlier, our baselines are CPUs and GPUs that we're extremely familiar with. So we know CPUs are good for handling complex workloads, while GPUs have acceleration for massively parallel workloads. So just as a key, the green blocks are for compute, blue and purple are for local memory, the yellow blocks are for control, and orange blocks are off-chip memory. So the reason why I'm bringing these two architectures up is to use them as reference points so we can look at some custom accelerators. So first we have tensor processing units, or TPUs, from Google. And each TPU version 3 chip includes 2 tensor cores, each of which uses systolic arrays for mixed precision matrix multiplication. Additionally, each tensor core also efficiently utilizes their HBM with embedding accelerators and pipeline execution. Next, we have intelligence processing units, or IPUs, from GraphCore. So what's so interesting about IPU's architecture is how much local memory it has. So for its second generation chip, it has 900 megabytes of SRAM. To efficiently organize this massive amount of SRAM, IPUs are split into thousands of individual tiles, each operating on its own instruction and data stream. So IPUs are actually super fast when everything fits on chip. And that's actually feasible when you have multiple chips on a board or in a pod. However, since IPUs are designed around SRAM access, DRAM access has to be manually managed, which makes execution quite challenging. So if we take a step back and look at all these architectures, we see how a wide range of use cases, like the different representations we introduced earlier, can be supported and accelerated. So here's some highlights of how they interact with the representations we just saw. So for each embedding representation, we evaluate speed up against a baseline of running embedding tables on CPUs. So we use a Broadwell server for CPU and V100 for GPU. And for the accelerators, we evaluate a different number of nodes. So for IPUs, there's chip, board, and pod levels. And TPUs, there's core, chip, and board levels. And what I want to show is for embedding tables, we see that TPUs are optimal for using because they have this custom and TPU embedding software layer. And this software layer is good for using the embedding lookup accelerator and optimizing pipeline execution. And interestingly, when there's only one IPU chip, embedding table execution, it just suffers greatly. So it's too low to show since we're forced to access DRAM. And for DHE, the small compute representation, we see that IPUs offer best acceleration. This is because DHE models are tiny and really fit onto IPU local memory. And again, hybrid execution path, which uses both, is somewhere in between table and DHE, as it just uses a lot of resources. So for more characterization, especially on energy efficiency, like see the paper. So far, we're left with, we have all these different representations above, on top of tables and different hardware. But how do we use all of this together to serve more and better quality recommendations? The last component I want to talk about is multi-path recommendation, where individual representations can dynamically be activated on target hardware. So this will allow us to balance both performance and accuracy for better overall recommendation serving. So let's take a closer look at how we implement multi-path recommendation. So first we look at the set of feasible hardware platforms. So for example, we can have a single CPU, a CPU-GPU system, each with different amounts of storage available. And based on the available memory capacity, we can start to train and identify representations that fit within my capacity budget. So for example, for an edge device with limited capacity, we'll opt for DHE, since they're in a megabyte scale. For larger platforms, we can look for hybrid configurations that utilize both memory and compute. And after we identify the set of available models, we map all the target representations onto available hardware. So how do we decide which representation hardware combination to activate? The answer is, it's actually really not up to us. So we have to look at input query characteristics. What is the SLA latency target? We need to consider this because query serving use cases are bound by these latency targets. Even if we want to use something like hybrid that gives us the best accuracy, if the execution time goes beyond SLA latency, we can't do that. We also need to consider query size. So representation execution times, they scale differently with query size. And hardware accelerators also have varying parallelization capabilities. So with these query level information, we can activate a specific path to generate embeddings. In this case, we decided to use hybrid on GPU. And then with these embeddings, we can serve your recommendations by running the rest of the model. So another component that we cover more in depth in the paper is a proposed software cache called MP cache. So at a high level, the cache exploits access locality and value similarity. So this super compute heavy stack doesn't have to be executed for every query. So now let's see how this multi-path execution paradigm works with MP cache. So here we evaluate a query serving scenario where queries following a log normal distribution have to be served under a strict latency target. So the metric that we care about is throughput of correct predictions. So we care about not only serving tons of predictions, but also serving the correct ones. So we evaluate a CPU-GPU system for both curtail Kaggle and a larger curtail terabyte use case. So for each of the use cases, we see different ones, like using tables on CPUs, tables on GPUs, and then the DHE and hybrid on GPUs. And we allow for embedding tables switching between CPU and GPU, and the best one, which is MP-Rec, where we allow for switching between CPUs, GPUs, and all the cool representations we saw earlier. So for Kaggle, we see that purely using GPUs for embedding tables actually is slightly worse for query serving. This is because Kaggle is a relatively lightweight model, so small queries actually sometimes prefer CPU execution. For executing DHE and hybrid, we see a significant degradation since these representations take too long to finish. And this leads to both longer execution times, lower throughput, and also queries just not meeting SLA latency target. So if we're limited to just using embedding tables, but we try this like CPU, GPU switching mechanism, we see better performance than using exclusively CPUs and GPUs. But for MP-Rec, lastly, we see the best performance. This is because after enabling MP cache, we're able to switch between all the different types of representations and hardware to execute high accuracy representations. So for Terabyte, we see similar trends. Actually, MP-Rec's impact is even more pronounced, given how Terabyte is a harder model to run. So, and when we integrate IPUs into query serving, assuming their software challenges are addressed, we see even higher throughput of correct predictions. So in this talk, we looked at a new hybrid representation that is costly for systems, but produces high quality embeddings, the representation as a design space, how we would go about mapping representations onto accelerators, and also using multipath recommendation to exploit these options. But if there's something for you to remember from this talk, it's this. So representation as a design space, it really unlocks systems and algorithmic benefits. And one way to accomplish this is through multipath recommendation. So for more in-depth discussions on how we map the workloads onto accelerators, different sensitivity studies, and instructions on how to set up and run all these representations for yourself, please check out the paper. Thank you.